Hello there and welcome to Mysteries Beneath Earth, a place where we allow the noise of the day to fade into the background, replaced by the slow, steady rhythm of curiosity. Tonight, I want to invite you to do something very simple, something humans have done for as long as we have had eyes to see and minds to wonder. I want you to imagine stepping outside, away from the glow of streetlights and screens, and looking up. Imagine the night sky not as a flat tapestry of darkness punctuated by points of light, but as a deep, three-dimensional ocean. An ocean without a surface and without a floor, stretching out in all directions, vast, silent, and terribly cold. When we look at this void, our instinct is to feel small. We see the stars as distant nuclear fires, and the space between them as empty, dead, and sterile. We think of Earth, our little blue marble, as a fortress of life, a lonely island where biology happened by a miraculous accident, surrounded by a hostile universe that wants nothing more than to freeze or burn us. But what if that intuition is wrong? What if the universe is not a desert, but a garden? What if the space between the stars is not empty, but filled with the invisible seeds of potential? Tonight, we are going to explore an idea that turns our understanding of biology upside down. It is an idea that suggests the Earth is not a creator of life, but a cradle, a nursery that caught a drifting seed from the dark and warmed it until it bloomed. This is the hypothesis of panspermia. It asks a single, shivering question: what if we are all, in the most literal sense, aliens? Before we drift into the science of meteorites and microbes, we have to settle into the history of this thought. Because the idea that life rains down from the sky is much older than modern astronomy. It whispers to us from the very beginning of philosophy, 500 years before the Common Era. In the sun-drenched lands of ancient Greece, a philosopher named Anaxagoras looked at the world differently than his peers. While others were trying to explain the world through the elements of earth, air, fire, and water, Anaxagoras proposed something more subtle. He spoke of spermata seeds. He suggested that the universe was composed of infinitely small, invisible seeds of all things. Flesh, bone, gold, stone, and life itself were present everywhere in the cosmos, floating in the ether, waiting for the right conditions to congregate and become visible. To him, life did not spring from nothing. It was rearranged from the eternal materials of the universe. Everything, he said, is in everything. It was a poetic thought, but for centuries, it was overshadowed by a different belief, one that seems almost laughable to us now: spontaneous generation. For nearly 2,000 years, the smartest people on Earth believed that life simply appeared. If you left meat out, maggots appeared. Therefore, dead meat created living maggots. If you left grain in a dark corner, mice would appear. The mud of the Nile River was thought to spontaneously transform into crocodiles when the sun hit it just right. It wasn't until the 19th century that this illusion was shattered. The great French chemist Louis Pasteur, with his swan-necked flasks and rigorous patience, proved once and for all that life only comes from life. He boiled broth to kill everything in it, and as long as he kept new dust and air from touching it, the broth remained sterile forever. No new life appeared. Spontaneous generation was dead. But Pasteur's victory created a new, deeper mystery. If life can only come from life, where did the first life come from? If you trace the chain of parents back, human to ape, ape to mammal, mammal to reptile, fish, worm, microbe, you eventually hit a wall. At some point, the chain has to start. At some point, dead matter must have become living matter. If Pasteur was right, and life cannot arise from non-life, then life on Earth must have come from somewhere else. This is where the door to the cosmos creaks open. In the late 19th century, science began to look at the Earth not as a closed room, but as a house with the windows blown open. The German physicist Hermann von Helmholtz and the British physicist Lord Kelvin, the man who formulated the absolute temperature scale, began to speak of meteorites. Lord Kelvin, a man of rigorous mathematics and thermodynamics, stood before the British Association for the Advancement of Science in 1871 and said something that shocked the room. He asked them to imagine the aftermath of a massive collision, worlds smashing together in space, shattering into fragments. He proposed that these fragments, these moss-grown ruins of other worlds, could drift through space carrying the seeds of life. We must regard it as probable in the highest degree, he said, that there are countless seed-bearing meteoric stones moving about through space. Imagine the image he planted in their minds. Not a universe of lonely biological accidents, but a universe of connection. A universe where a dying world could pass the torch of life to a new one. A universe where life is not a fleeting spark, but a fire that spreads from hearth to hearth. But how? How could anything survive the journey? Space is not merely empty, it is violent. There is the vacuum which boils water instantly. There are temperatures near absolute zero. There is the searing ultraviolet light of the stars and the invisible DNA-shredding bullets of cosmic rays. To suggest that a living cell could float through that hellscape and arrive safely on Earth seemed, to many, like a fantasy. Yet, the idea refused to die. It lingered in the back of the scientific mind, a ghost story that felt too plausible to ignore. And as we moved into the 20th century, we began to realize that life is far tougher, far stranger, and far more stubborn than we had ever given it credit for. We started finding life in the boiling acid springs of Yellowstone. We found it crushed under the pressure of the deepest ocean trenches, feeding on poison. We found it frozen in Antarctic ice, sleeping for eons only to wake up when warmed. If life could survive the hellish environments of Earth, why not the void of space? This is the journey we are embarking on. It is a detective story that spans billions of years. The clues are hidden in the dust of comets, in the twisted chemistry of ancient rocks, and in the genetic code of our own bodies. Tonight, we are not just asking how life began. We are asking where we belong. Are we children of the Earth, molded solely by this planet's clay? Or are we wanderers, the descendants of travelers who crossed the great dark ocean of the Milky Way to find a home here? To answer that, we have to leave the safety of the atmosphere. We have to drift out into the silence, where the sunlight is unfiltered and the wind is made of particles. We have to look at the mechanism of travel. If life moves from star to star, what is the ship? The first scientific answer to that question was as beautiful as it was controversial. It didn't involve rocks or spaceships. It involved light. So, settle in. Pull the blankets up a little higher. We are about to catch a ride on a sunbeam and see if it can carry the weight of a living world. When we think of the forces that move things in the universe, we usually think of the heavy hitters: gravity, magnetism, the explosive force of a supernova. We rarely think of light as something that can push. Light feels intangible to us. It illuminates, it warms, but it doesn't feel like a wind. You don't feel a pressure against your chest when you step out into the morning sun. But in the early years of the 20th century, a Swedish physicist named Svante Arrhenius looked at light and saw something powerful. Arrhenius was a giant in the scientific world. He was the man who first calculated how carbon dioxide warms the planet, essentially discovering the greenhouse effect. He had a mind that could see the subtle, invisible connections between chemistry and physics. And in 1903, he turned his gaze to the problem of panspermia. Arrhenius wasn't satisfied with Lord Kelvin's idea of moss-grown rocks. Rocks were heavy. Rocks were rare. Rocks required violent collisions to get moving. Arrhenius wanted a mechanism that was constant, elegant, and universal. He published a book called Worlds in the Making in 1908, and in it, he proposed a theory that came to be known as radiopanspermia. The concept is breathtakingly simple. Light has momentum. It doesn't have mass, but it carries energy, and when it hits a surface, it imparts a tiny, microscopic push. This is known as radiation pressure. On the scale of a human or even a grain of sand, this pressure is negligible. It's like trying to move a mountain by breathing on it. But Arrhenius calculated that if a particle were small enough, say, the size of a single bacterial spore, a mere fraction of a micron across, the pressure of sunlight would be enough to overcome the gravity of a star. Imagine a comet swinging close to the sun. As its ice heats up and sublimates into gas, it releases tons of dust and debris into space. Arrhenius suggested that among this debris could be millions of bacterial spores lifted from the atmosphere of a living planet. Once these spores drifted high enough, the pressure of the sun's light would catch them, like wind catching a dandelion seed. That he did the math. He calculated that a spore, pushed by the light of our sun, could cross the orbit of Mars in weeks, could reach Jupiter in months, and, given enough time, it could be pushed right out of the solar system, riding the solar wind into the deep interstellar void. It is a romantic image. The galaxy as a dandelion field, with stars blowing seeds across the dark, trading life in a silent, luminous exchange. According to Arrhenius, life didn't need violent asteroid impacts to spread. It just needed light. Every star in the universe was a potential engine of dissemination, pushing the spores of its planets out into the cosmos. But a beautiful theory is like a soap bubble. It is lovely to look at, but it pops easily when it touches the sharp edge of reality. And the sharp edge for radiopanspermia was the environment of space itself. Arrhenius knew space was cold, but he wasn't worried about the cold. He knew that spores on Earth could survive freezing temperatures, entering a state of suspended animation called cryptobiosis. In this state, biological time stops. The machinery of the cell shuts down, the water is expelled, and the organism becomes effectively a crystal, waiting for warmth to return. However, Arrhenius did not fully understand what else was out there. In the decades after his book was published, our understanding of the space environment grew darker. We discovered that the sun does not just emit visible light. It emits ultraviolet radiation, UV rays, and beyond the sun, the galaxy is filled with cosmic rays, high-energy particles that tear through matter like microscopic bullets. This was the death knell for the classical idea of radiopanspermia. A naked spore, floating alone in the vacuum, would be exposed to the full, unfiltered glare of the sun. UV radiation destroys DNA. It shatters the chemical bonds that hold the code of life together. Within minutes or perhaps hours of leaving an atmosphere, a single spore would be sterilized. It wouldn't be a seed anymore, it would be a husk. The critics of panspermia seized on this. They pointed out that the very force Arrhenius relied on, the light, was also the killer. To ride the light, you had to be small. But if you were small, you had no shielding. You were naked against the radiation. It seemed like a catch-22 of cosmic proportions. For a long time, this objection pushed panspermia to the fringes of science. It became the realm of science fiction, not serious biology. The math didn't seem to work. The survival rates were effectively 0. But science is stubborn. It doesn't give up on a good idea just because of one obstacle. Researchers began to wonder, does a seed have to be naked? What if it has a coat? What if it has a vehicle? This line of questioning brought us back to Lord Kelvin's Smashing Worlds, but with a modern twist. We moved from radiopanspermia, travel by light, to lithopanspermia, travel by stone. The logic is compelling. If a single bacterium cannot survive the UV glare, what about a colony of bacteria hiding inside a rock? Rock is an excellent shield. Just a few centimeters of stone can block out UV radiation entirely. A few meters of stone can dampen even the high-energy cosmic rays. But this creates a new problem. How do you get a rock off a planet? You can't just float a boulder on a sunbeam. You need energy, massive amounts of it. You need an event so violent that it launches mountains into the sky. We know these events happen. We see the craters on the Moon, on Mars, and even on Earth. We know that asteroids slam into planets with the force of millions of nuclear bombs. When an asteroid hits, it acts like a splash in a pond. It digs a crater, and the debris from that crater is ejected outward in a cone. Some of that debris moves so fast, reaching escape velocity, that it leaves the planet entirely. This was the new model. Life doesn't drift. It is blasted. It hitchhikes inside the debris of catastrophe. But consider the violence of that moment. Imagine you are a microbe living in a rock on the surface of ancient Mars. Suddenly, a 10-kilometer asteroid strikes. The ground liquefies. The shockwave travels through the rock at thousands of meters per second. The pressure spikes to levels that turn graphite into diamond. The temperature soars. Then you are flung upward through the atmosphere into the vacuum, accelerating from 0 to escape velocity in seconds. Could anything survive that? It seems impossible. It seems like trying to survive a direct hit from a cannonball while being inside the cannonball. And yet, we have tested it. In laboratories, scientists have used giant gas guns to fire projectiles at targets, simulating the shock of an asteroid impact. They placed layers of bacteria between the rocks. And to everyone's astonishment, some of them survived. It turns out that if the rock is near the surface of the impact zone, it is not melted. It is spalled, ejected by the interference of shock waves in a way that keeps it relatively cool. It's a phenomenon where the pressure is high, but the temperature doesn't have time to cook the interior of the rock. The bacteria inside are shaken, compressed, and terrified, perhaps, but they are not incinerated. So the mechanism exists. We have the engine impacts, we have the vehicle meteorites, and we have the shield stone. But once the rock is in space, the journey has only just begun. The rock might float for 1 million years. It might float for 10 million. Inside, the microbes sit in the dark, freezing cold, slowly accumulating damage from the background radiation of the galaxy. It is a silent, lonely endurance test. And then the final hurdle, arrival. The rock has to hit another atmosphere. It has to endure the fireball of re-entry, where the air in front of it turns to plasma hotter than the surface of the sun. It has to slam into the ground, surviving a second impact. It sounds like a sequence of impossible miracles. The launch, the transit, the entry, the landing. If any one of them fails, the chain is broken. But here is the thing about the universe. It has time. It has billions of years. And it has billions of rocks. Even if the chance of success for one rock is 1 in a billion, if you throw 1 trillion rocks, life finds a way. And we know the rocks make the journey. We have held them in our hands. We have found rocks in Antarctica that are chemically identical to the atmosphere of Mars. We know that Earth and Mars have been swapping spit, swapping rocks, for eons. The question is no longer, can the rocks travel? The question is, was there anyone on board? To answer that, we have to look at the passengers. We have to look at the limits of life itself. How tough is biology? Can it really sleep for 1 million years? Can it eat radiation? Can it survive the vacuum? The answers we found on Earth were not what we expected. We found creatures that seemed to have been built for the void, long before they ever left the ground. Creatures that defy the rules of life and death. Let's descend from the cold of space for a moment and look into the microscope at the tiny, indomitable monsters that might be the astronauts of the microbial world. We established earlier that light, for all its poetic beauty, carries a hidden blade. The ultraviolet radiation that floods the space between stars acts as a universal sterilizer, stripping apart the delicate molecular machinery of any exposed cell. If life is to move from one world to another, it cannot simply float on the solar wind like a dandelion seed. It needs armor. It needs a shield thick enough to block the radiation, sturdy enough to withstand the vacuum, and massive enough to hold its own against the cold. Nature, it turns out, provides exactly such a shield. It is the most common material in the universe after gas and dust. It is rock. This brings us to the second great variation of our hypothesis, Lithopanspermia. The prefix litho comes from the Greek word for stone. If radiopanspermia is the idea of life drifting on light, Lithopanspermia is the idea of life hitchhiking inside mountains. It suggests that the true spaceships of the universe are not built of metal and engineered by minds, but are hewn from the crust of planets by the brute force of physics. But this introduces a problem of immense scale. A bacterium is light. Lifting it requires only a breath of air. A rock capable of shielding life, a rock perhaps 1 meter across, weighing tons, is heavy. Gravity is a jealous guard. It does not like to let things go. To get a rock off the surface of the Earth and into deep space, you need to achieve escape velocity. For our planet, that means accelerating an object to over 11 kilometers per second. That is 40,000 kilometers per hour. There is no gentle way to do this. You cannot throw a rock that fast. Volcanoes, even the mightiest supereruptions in Earth's history, do not have the power to eject stones clear of the planet's gravitational pull. They can reach the upper atmosphere, yes, but gravity always drags them back down. To escape a planet, you need violence. You need an event that imparts so much energy in such a fraction of a second that the crust itself becomes a projectile. You need an asteroid impact. Let us slow down time and imagine the mechanics of such a launch. Picture a quiet landscape on a prehistoric Earth, or perhaps a wet, early Mars. A rock the size of a city is falling from the sky. When it strikes, it does not just break the ground. It behaves like a fluid. The solid crust ripples. The energy release is equivalent to millions of nuclear weapons detonating at a single point. In the center of the crater, the heat is absolute. Rock vaporizes instantly. Nothing biological can survive there. Any life at ground zero is reduced to its constituent atoms in a nanosecond. If this were the only mechanism, panspermia would be a dead end. But physics is full of loopholes. The destruction is not uniform. As the shockwave radiates outward from the impact zone, it interacts with the surface layers of the crust in a phenomenon known as spallation. Imagine hitting a dusty rug with a stick. The dust flies up not because you touched the dust, but because the shock transferred through the rug kicked it loose. In a planetary impact, the interference of shock waves near the surface can launch massive boulders upward without compressing them to the point of melting. These rocks are flung toward the sky at hypersonic speeds, riding the edge of the expanding vapor plume. They punch through the atmosphere in seconds, moving so fast they glow like inverted shooting stars. And inside these rocks, the temperature remains surprisingly low. While the exterior might be scorched, the interior, insulated by the poor conductivity of stone, might only experience a brief flash of heat, or perhaps no significant heating at all. The microbes hiding in the microscopic fissures of that rock are shaken, subjected to immense G-forces, but they are not cooked. Suddenly, the noise stops. The vibration ends. The blue sky fades to the black of space. The rock, torn from the surface of its mother world, is now a traveler. It has become an arc. This is the arc of rock. Inside, the conditions have shifted from a warm, wet planetary surface to the freezing vacuum of the void. The water in the rock's pores freezes, locking the bacteria into a suspended state. They are now astronauts, encased in a natural sarcophagus that protects them from the very things that killed the naked spores in Arrhenius's theory. The rock spins slowly as it drifts. When the sun hits it, UV radiation strikes the surface, but it penetrates only a few millimeters. The deadly cosmic rays, moving at nearly the speed of light, dig deeper, but a rock a few meters thick can absorb much of that punishment. The life inside is safe, or at least safer. But where is it going? This is the terrifying part of Lithopanspermia. There is no pilot. There is no navigation. The rock is a slave to orbital mechanics. It enters an orbit around the sun, crossing the paths of other planets, swinging through the emptiness for eons. It might drift for 1,000 years. It might drift for 1,000,000. It might drift for 1 billion. During this time, the biology inside must wait. It must endure a silence longer than the existence of the human species. And this raises a crucial question. Can life actually wait that long? DNA degrades over time. Background radiation, the slow decay of atoms within the rock itself, eventually breaks down the genetic code. If the journey takes too long, the passenger arrives dead. However, simulations show that rocks from Mars can reach Earth much faster than we might think. Some trajectories allow for a transit time of just a few months. Others take thousands of years. In geological terms, this is a blink of an eye. And we know this happens. This is not speculation. We have found the arcs. If you go to the ice fields of Antarctica or the deserts of North Africa, and you know what to look for, you can find rocks that do not belong to this world. We have collections of meteorites, the SNC meteorites, that contain trapped bubbles of gas. When we analyze that gas, the ratio of isotopes matches the atmosphere of Mars perfectly. We have held pieces of the red planet in our hands. We know for a fact that rocks can be blasted off one planet, float through space, and land intact on another. The transport mechanism is real. The bus route exists. The only missing piece of the puzzle is the passenger. Did those rocks carry life? And if they did, could that life survive the final, violent act of the journey? The arrival? Because what goes up must come down. The ark must enter the atmosphere of a new world. It hits the air at 20, 30, maybe 50,000 kilometers per hour. The friction turns the air in front of it into plasma. The outer layer of the rock melts, shedding liquid stone in a trail of fire. This is the fusion crust we see on meteorites, a black, glassy rind formed by the heat of entry. But again, rock is a stubborn insulator. The heat of re-entry is intense, but it is brief. It lasts only for a minute or two. The heat does not have time to soak all the way to the center. A meteorite can land on the ice of Antarctica, possessing a fusion crust that is hot to the touch, while the inside is still frozen solid from the chill of deep space. The rock hits the ground, cracks open, the ice inside melts, and the sleepers, the tiny microbial passengers who have been frozen for 1,000,000 years, taste liquid water for the first time since they left home. They wake up. They begin to divide. This is the mechanism of Lithopanspermia. It paints a picture of a solar system that is not a collection of isolated planets, but a connected archipelago where materials and perhaps biology are constantly being exchanged, carried across the dark water of space on rafts of stone. But a raft is useless if the passenger dies of exposure. We have spoken of the shield, and we have spoken of the journey. Now we must speak of the biology itself. Is there really anything on Earth or anywhere else that can survive being frozen, irradiated, and blasted into the void? As it turns out, life is not as fragile as we think. In fact, some of the creatures living quietly in your backyard right now might be better suited for space travel than they are for Earth. When we look at a human being, we see a fragile thing. We need a very specific range of temperature. We need air with 21% oxygen. We need water every few days. We are soft, easily broken, and terribly vulnerable to radiation. If you put a human in the vacuum of space without a suit, unconsciousness comes in 15 seconds. Death follows shortly after. Because we are fragile, we assume life is fragile. We look at the hostility of the cosmos, the vacuum, the freezing cold, the searing radiation, and we think, nothing could live there. But we are looking at life through the lens of our own limitations. On this planet, hidden in the soil, floating in pond scum, and dwelling in the radioactive waste of nuclear reactors, are organisms that seem to defy the laws of biology. We call them extremophiles, lovers of the extreme. And when we study them, we begin to wonder if they were built for Earth at all, or if they are carrying the dormant toolkits of a cosmic traveler. Let's start with a champion of endurance, a bacterium with the nickname Conan the bacterium. Its scientific name is Deinococcus radiodurans. This microbe was discovered not in a rainforest or a deep-sea vent, but in a can of spoiled meat that had been sterilized with gamma radiation. Scientists thought they had killed everything in the can. But Deinococcus was still there, happily dividing. When researchers looked closer, they found something astonishing. If you blast a human cell with radiation, the DNA, the long, twisted ladder that holds our genetic instructions, shatters. It breaks into hundreds of pieces. The cell cannot read the instructions anymore, and it dies. When you blast Deinococcus with the same radiation, even doses 1,000 times higher than what would kill a human, its DNA also shatters. But Deinococcus doesn't die. It simply pauses. Within a few hours, it stitches its DNA back together. It has multiple copies of its genome and an enzyme repair system so efficient it can reassemble the shredded code perfectly, without a single error. Why does a bacterium on Earth possess this superpower? Natural levels of radiation on Earth are low. There has never been a time in Earth's history where radiation levels were high enough to require this kind of defense. Evolution usually operates on the principle of use it or lose it. Why evolve a shield for a weapon that doesn't exist on your planet? Some scientists suggest it is a side effect of surviving dehydration, but others look at Deinococcus and see a creature pre-adapted for space. Its repair mechanisms are exactly what you would need to survive the cosmic rays during a million-year journey inside a rock. But Deinococcus is not alone. There is another creature, far more charismatic, that has become the poster child for panspermia. The tardigrade, also known as the water bear. These are microscopic animals, not bacteria. They have 8 legs, little claws, and a face that looks vaguely like a vacuum cleaner. They live in moss and lichen, perhaps even in your garden. They are adorable in a microscopic sort of way, but they are also indestructible. When a tardigrade faces hard times, when the water dries up, it does something magical. It curls up into a tight ball called a ton. It expels almost all the water from its body and replaces it with a special sugar that turns the inside of its cells into a kind of glass. Its metabolism drops to 0.01% of normal. In this state, the tardigrade is not technically alive, but it is certainly not dead. It is paused. It has stepped outside the flow of time. In this ton state, tardigrades have been boiled in alcohol. They have been frozen to almost absolute zero. They have been crushed under pressures higher than the bottom of the ocean. And most importantly for our story, they have been taken into space. In 2007, the European Space Agency attached a box of sleeping tardigrades to the outside of a Photon M3 rocket. They were launched into orbit and exposed to the hard vacuum of space. For 10 days, they floated in the void. There was no air. The temperature swung wildly between freezing shadow and boiling sunlight. They were bombarded with the full spectrum of solar UV radiation, the light that Arrhenius's critics said would kill anything. When the capsule returned to Earth, the scientists rehydrated them, and the water bears simply woke up. They uncurled, crawled away, ate, and laid eggs as if nothing had happened. The babies that hatched from those eggs were healthy. They had survived the vacuum. They had survived the radiation. They had survived the impossible. Experiments like this have continued on the International Space Station. The exposed facility is a small box bolted to the outside of the station, a torture chamber for biology. We have put lichen, bacteria, and seeds inside it. We have left them there for 18 months. The results are consistently humbling. While many die, some always survive. Certain lichens from the Antarctic adapt to the vacuum instantly. Their cells go dormant, their pigments act as sunscreen, and they wait. When brought back in, they resume photosynthesis within hours. But perhaps the most haunting story of survival comes from the Apollo era, a mystery that blurs the line between science and accident. In 1967, the unmanned Surveyor 3 spacecraft landed on the moon. It sat there in the ocean of storms for 2.5 years, exposed to the brutal lunar cycle, 2 weeks of boiling day, 2 weeks of freezing night, With no atmosphere to protect it. In 1969, the astronauts of Apollo 12 landed nearby. They walked over to the dead robot and used shears to cut off its camera, bringing it back to Earth for analysis. When scientists examined the camera in a sterile lab, they claimed to find something shocking. Inside the camera body, trapped in a piece of foam insulation, they found a colony of Streptococcus mitis, a common bacterium found in the human nose and throat. The bacteria were alive. The implication was staggering. Had these bacteria been sneezed onto the camera by an engineer in a clean room before launch? Had they survived the launch, the 3-day vacuum transit, and then sat on the moon for 30 months? Had they endured the radiation and the temperature swings, only to wake up when they returned to Earth? For decades, this was held up as the ultimate proof of panspermia. If bacteria could survive the moon for 2 years in a camera, they could survive a meteorite for 1,000,000 years. Today, modern analysis suggests it might have been a breach of protocol in the lab after the camera returned, that the contamination happened on Earth, not before launch. We may never know for sure, but the very fact that it was plausible, that the scientific community could believe it was possible, shows how far our understanding has shifted. We no longer view life as a delicate candle flame that is easily snuffed out. We view it now as a dormant fire, capable of banking its coals and waiting out the long, dark winter of space. The survivors of the void tell us that the biological hardware for space travel already exists. We don't need to invent sci-fi aliens with thick lead skin. The moss on your roof and the bacteria in your soil already possess the toolkit to survive the journey between worlds. So we have the mechanism, the arc of rock. We have the passengers, the extremophiles. The theory of panspermia is mechanically and biologically sound. But a theory needs more than "it's possible." It needs evidence. It needs a smoking gun. And in 1969, the same year humans walked on the moon, the universe decided to drop a gift right into our laps. A fireball tore through the sky over Australia, bringing with it a smell that would change chemistry forever. This was the Murchison meteorite. And what we found inside it didn't just suggest life could survive in space. It suggested that the very ingredients of life might be made there. On a cool Sunday morning in late September 1969, the universe decided to knock on our door, not with a whisper, but with a sonic boom that rattled the windows of a small village in Victoria, Australia. The sky split open. A fireball, glowing with the fierce friction of the atmosphere, tore apart as it screamed toward the ground. It wasn't a single rock anymore. It was a shotgun blast of stones raining down on the quiet rural community of Murchison. Locals who ran outside didn't just see the smoke trails. They noticed something else immediately, something strange. The air didn't smell like burnt rock or ozone, which is typical for lightning or stone. It smelled strong, pungent, and distinctly chemical. Witnesses described it as smelling like methylated spirits, or perhaps tar, or even rotting compost. It was a smell that belonged in a biology lab or a swamp, not falling from the sterile vacuum of space. They gathered the stones, black, charcoal-like rocks that crumbled easily in the hand. They didn't know it yet, but they were holding the oldest things any human had ever touched. These rocks, now known as the Murchison meteorites, were carbonaceous chondrites. They were time capsules formed in the very first moments of the solar system, 4.5 billion years ago, before the Earth had even finished cooling. They were pristine samples of the cloud of dust and gas that gave birth to the sun. When scientists finally got these stones into the laboratory, what they found inside shattered the boundary between astronomy and biology. They dissolved the core of the meteorite, careful to avoid any contamination from earthly dust, and ran the resulting solution through a chromatograph to see what it was made of. They were expecting minerals. Iron, nickel, silicates, the stuff of geology. But the machine spit out a different signal. It detected amino acids. To understand the gravity of this, we have to remember what an amino acid is. They are often called the building blocks of life. But that phrase is so overused it loses its punch. Think of them instead as the letters of a cosmic alphabet. Proteins, the complex machines that run your body, are just long sentences written using these letters. Your muscles, your enzymes, your hemoglobin, they are all stories written in amino acids. For a long time, we assumed that Earth was the only place where these letters were written. We thought the chemistry of space was too simple, too harsh, too dead to create complex organic molecules. But the Murchison meteorite proved us wrong. Inside that rock were over 70 different types of amino acids. Crucially, many of them were types that do not exist in life on Earth. We use a specific set of 20 amino acids to build our bodies. Murchison contained those, yes, like glycine and alanine, but it also contains strange alien cousins, isovaline and pseudoleucine, molecules that nature on Earth simply doesn't use. This was the smoking gun. It proved that the smell the villagers noticed wasn't contamination from the Australian soil. It was the smell of deep space. The implications are staggering. It means that the universe is not a vast, empty room. It is a factory. In the dark, cold clouds between the stars, simple atoms of carbon, hydrogen, and nitrogen are clicking together, driven by starlight and shockwaves, forming the complex Lego bricks of biology. The Murchison meteorite taught us that the ingredients for life are not special miracles reserved for Earth. They are common. They are falling from the sky all the time. Every time you look up at a shooting star, you might be watching a delivery of prebiotic soup burning up in the atmosphere. This discovery shifted the conversation of panspermia from life to prebiotic chemistry. Maybe the seed that arrives isn't a fully formed cell. Maybe it's a kit. Maybe the Earth didn't need to invent the chemistry of life from scratch. Maybe the universe delivered the parts and Earth just assembled them. But chemistry is one thing, biology is another. Amino acids are not alive. They are just complex dust. Finding a brick is not the same as finding a house. To find evidence that actual living organisms might have traveled between worlds, we had to look closer to home. We had to look at our neighbor, the rusty, dust-choked world of Mars. Mars holds a special place in the imagination of panspermia because it is the only other planet we know of that was once truly like Earth. Billions of years ago, while Earth was still a molten, toxic nightmare, Mars was already cooling down. It had oceans of liquid water. It had a thick atmosphere. It had blue skies. If life is a race, Mars had a head start. It is entirely possible. And this is a thought that keeps planetary scientists awake at night, that life began on Mars first. Imagine a scenario for a billion years ago. Mars is thriving. Simple microbes are swimming in its shallow seas. But Mars is smaller than Earth. Its gravity is weaker, and its magnetic field is dying. The atmosphere begins to strip away. The planet starts to freeze. But before the end, a massive asteroid slams into the Martian surface. Debris is launched into space. Millions of rocks, carrying the frozen, dormant spores of the dying Martian biosphere, drift inward toward the sun. Eventually, they cross the path of the blue planet next door. They rain down on the sterile oceans of early Earth. They melt. The Martian microbes wake up, find a whole new world of water and sunlight, and begin to multiply. If this story is true, then we are the Martians. The life on this planet is just the refugee colony of a dead world. This sounds like pure science fiction until you look at the story of a specific rock named ALH 84001. The name is unpoetic, standing for Allen Hills, 1984, sample 001. It was found in the biting winds of Antarctica, a place that is the closest analog to space on Earth. Meteorites are easy to find in Antarctica because the ice floes act like a conveyor belt, gathering stones that fall over thousands of years and depositing them in stranding zones against the mountains. And against the white ice, a black rock stands out like a beacon. LH 8400 once sat in a storage locker for years before anyone realized what it was. It was a piece of volcanic rock, gray and unassuming, but gas analysis proved it was from Mars, and radioactive dating showed it was incredibly old, crystallizing from magma 4.5 billion years ago. It had sat on Mars for billions of years, witnessed the wet era, and then was blasted off into space about 16 million years ago. It drifted, lonely and frozen, until it fell onto the ice of Antarctica 13,000 years ago. In 1996, NASA dropped a bombshell. They announced that they had found something inside this rock. Not just amino acids, but fossils. The world stopped. President Bill Clinton gave a press conference on the South Lawn of the White House. "It speaks of the possibility of life," he said. "If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered." What had they found? Deep inside the fissures of the rock, under the electron microscope, scientists saw strange structures. They saw carbonate globules, minerals that usually form in the presence of liquid water. They saw tiny crystals of magnetite, a magnetic mineral. On Earth, some bacteria produce magnetite crystals of a very specific size and shape to help them navigate, like an internal compass. The crystals in the Mars rock looked identical to the ones made by bacteria on Earth. But most shockingly, they saw shapes. Tiny, segmented, worm-like tubes. They looked exactly like fossilized bacteria, only much, much smaller. They looked like life. For a moment, it seemed the question was answered. We were not alone. The universe was teeming with life, hopping from rock to rock. But science is a brutal arena. As soon as the papers were published, the skeptics descended. They attacked every line of evidence. They argued that the worm shapes were too small to hold the machinery of a cell. They argued that the magnetite crystals could be formed by geological shock, not biology. They argued that the carbonate globules formed at temperatures too high for life. Over the last few decades, the consensus has softened. Most scientists today do not believe ALH 84001 contains conclusive proof of life. They believe the shapes are likely geological, tricking our eyes because we are desperate to see patterns. However, the rock did prove something else, something undeniable. Proved that Earth and Mars are not isolated systems. They are siblings who trade clothes. We know now that tons of Martian material falls on Earth every year. And tons of Earth material, blasted off by the asteroid that killed the dinosaurs, for instance, has landed on Mars. If life exists on one, it is almost impossible to keep it from contaminating the other. The planetary protection officers at NASA worry about us accidentally bringing Earth bacteria to Mars on our rovers. But nature has been throwing rocks at Mars for billions of years. If life can survive the trip, the contamination happened eons ago. This realization leads us to a broader, darker thought. Mars and Earth are close. They are in the same habitable zone warmth. But what about the visitors that come from much farther away? What about the travelers that don't belong to our solar system at all? The universe is not just rocks and planets. It is also filled with dirty snowballs, comets. These travelers spend most of their lives in the deep freeze of the Oort cloud, so far from the sun that the star is just a bright dot. They are the deep storage of the solar system. If meteorites are the rocky vessels of Panspermia, comets are the tankers. They carry the one thing life needs more than anything else: water. For a long time, we wondered where Earth's oceans came from. The Earth formed hot. Any water it had in the beginning would have boiled away. Yet here we are, a blue marble. The leading theory is that after the Earth cooled, it was bombarded by a storm of comets, the Late Heavy Bombardment. These icy impactors brought the water that now fills our oceans. But did they bring something else? In 2014, humanity did something extraordinary. We caught a comet. The Rosetta spacecraft, after a 10-year chase, entered orbit around Comet 67P/Churyumov-Gerasimenko. It dropped a lander, Philae, onto the surface. It was a gray, dusty, alien landscape. But as Rosetta sniffed the gas coming off the comet, it found the signature of organic molecules. It found glycine, that same amino acid found in Murchison. It found phosphorus, a key ingredient in DNA. It found a rich, dark crust of organic tars. Comets, it seems, are not just dirty snowballs. They are frozen reservoirs of the chemistry of life. And unlike rocky meteorites, which fall fairly often, comets are rare but massive. A single comet impact delivers a vast amount of energy, water, and organics all at once. Some scientists propose a model called cometary panspermia. They suggest that comets are the perfect incubators. As a comet approaches a star, its interior warms up. Pockets of liquid water might form deep under the icy crust, protected from the vacuum. In these temporary, dark, warm oceans, the chemicals could mix. Maybe life doesn't start on planets. Maybe it starts in the belly of a comet, and the comet then crashes into a planet, delivering not just the seed, but the water to nourish it. It is a chaotic, violent way to view our origins. We tend to think of ancestry as a tree, with roots going down into the earth. But panspermia suggests our roots go up. It suggests that the water in your glass and the carbon in your body were once floating in the dark between Jupiter and Neptune, frozen in a jagged mountain of ice waiting for gravity to pull it home. But we can zoom out even further. If the solar system exchanges material, what about the galaxy? For generations, astronomers assumed that solar systems were islands. The space between stars is so vast, light years of nothingness, that we thought matter could never cross the divide. A rock from another star system entering ours seemed statistically impossible. Then came October 2017. Telescopes in Hawaii picked up a faint, fast-moving object. It was tumbling, shaped like a cigar or a flattened disc, and it was moving too fast to be orbiting the sun. It wasn't from here. It had come from deep interstellar space, swooped around our sun, and was heading back out into the dark. We named it Oumuamua. a Hawaiian word meaning scout or messenger from afar. Oumuamua was a shock to the system. It proved that interstellar objects pass through our solar system. And if one passed through while we were looking, it implies that millions must have passed through when we weren't. Oumuamua was dry and rocky, but 2 years later, another visitor arrived, Borisov. And Borisov was a comet. It was spewing gas and dust, interstellar gas, interstellar dust. Think about what this means for panspermia. It means the galaxy is mixing. A star system on the other side of the Milky Way could explode or be hit by asteroids, ejecting rocks into the galactic current. Those rocks drift for millions, maybe billions of years. Eventually, one of them drifts through our system. Maybe it hits Earth. This is galactic panspermia. It suggests that life might not just be a local phenomenon, shared between Earth and Mars. It might be a galactic phenomenon. If life evolved once anywhere in the Milky Way, the asteroid impacts and the stellar winds would eventually spread it everywhere. The galaxy could be infected with life. This leads us to look at the dust itself. Not the rocks, not the comets, but the clouds. When we point our radio telescopes at the vast, dark clouds of the Orion Nebula, places where new stars are being born, we see spectral lines. We see the fingerprints of molecules absorbing light. And we don't just see hydrogen. We see ethanol, alcohol. We see sugars. We see buckyballs, complex carbon cages. We see PAHs, polycyclic aromatic hydrocarbons. The emptiness of space is full of smog. Organic smog. Two controversial scientists, Fred Hoyle and Chandra Wickramasinghe, took this idea to its extreme limit. In the 1970s, they looked at how interstellar dust absorbed light, and they noticed something strange. The way the dust blocked starlight matched the way dried bacteria block light in the lab. They proposed a theory that was ridiculed at the time and is still treated with extreme caution today. They suggested that the dust is bacteria. They argued that the vast clouds of the galaxy are not just chemical factories, but biological ones. That life is cosmic, that it exists in the vacuum on a massive scale, and that planets like Earth are just stations where this cosmic life settles down and evolves. Most astronomers think Hoyle went too far. They argue that the spectral match is a coincidence, that complex chemistry is not the same as biology. But the line is getting blurrier. We keep finding more complex molecules in space. We found molecules that look like the precursors to RNA in the center of the galaxy. Whether the clouds are alive or just filled with the potential for life, the conclusion is similar. We are not made of special stuff. The gold of biology, the carbon, the nitrogen, the water, the amino acids, is not rare. It is the dust of the universe. We are simply a part of the cloud that got dense enough to wake up and look around. But if the universe is throwing biological material at us, is it possible we can go out and catch it? Can we intercept the package before it hits the ground and burns up? In the last few years, we have stopped waiting for meteors to fall. We have started going to the source. We built robots, Hayabusa 2 from Japan and OSIRIS-RX from the United States, and sent them to catch asteroids in their natural habitat. These missions were daring. They had to fly millions of miles, match speed with a spinning mountain of rubble, and gently kiss the surface to suck up a handful of dust. When Hayabusa 2 returned its capsule to the Australian outback in 2020, and OSIRIS-RX dropped its sample in the Utah desert in 2023, scientists held their breath. These were not rocks that had been cooked by entry into Earth's atmosphere. These were pristine. They had been in the deep freeze of space for billions of years. And inside them, we found uracil. Uracil is one of the 4 letters of RNA. It is a nucleobase. Without uracil, there is no genetic code as we know it. And there it was, sitting in a rock that had never touched a planet. We also found vitamin B3. We found a symphony of organics. It was the final nail in the coffin of the idea that space is sterile. Space is a pantry. It is stocked with everything you need to bake a cell. But there is a version of panspermia that goes beyond rocks and comets. A version that asks a question about intent. All the theories we have discussed so far are accidental. A rock gets hit. A spore drifts. A comet crashes. It is a lottery. But what if the seed was sent on purpose? This is the hypothesis of directed panspermia. It was famously championed by Francis Crick, the man who, along with James Watson and Rosalind Franklin, discovered the structure of DNA. Crick looked at the complexity of the genetic code and felt a twinge of doubt. It seemed too perfect, too uniform. Why is the genetic code identical for a bacteria, a mushroom, and a human? If life evolved from a messy soup, wouldn't there be different codes, different startups competing? Crick wondered if life on Earth was too sophisticated to have evolved here in the short time available between the cooling of the crust and the first fossils. He proposed a thought experiment. What if an advanced civilization, facing the end of their own star, decided to preserve their biological heritage? They couldn't travel themselves, the distances were too great, but they could send bacteria. Bacteria are small, durable, and can be packed by the billions into tiny probes. You could launch millions of these probes in all directions, targeting young solar systems where liquid water might exist. The payload would be a packet of algae or cyanobacteria, something that could land in a sterile ocean, wake up, and start producing oxygen. Something that would terraform the planet and pave the way for evolution. It sounds like the plot of a movie, like Prometheus, but Crick argued it solved the timing problem. It explained why life appeared so quickly on Earth. It arrived ready-made. Of course, there is zero evidence for this. It also kicks the can down the road. If aliens seeded us, who created the aliens? But it forces us to look at ourselves, because we are currently standing on the precipice of becoming that civilization. We are already sending probes to Mars. We are talking about sending tiny laser-propelled sails to Alpha Centauri. We adhere to strict planetary protection rules to avoid contaminating other worlds, but those rules are for science. Eventually, the desire to spread life may overtake the desire to study it. Some ethicists argue we have a moral duty to spread life. If the universe is mostly dead, and we are one of the few candles burning, is it not our job to light other candles? To seed the galaxy with Earth life before our sun dies? We could be the engineers of the next directed panspermia. But this brings us to the dark side of the theory. If life can travel, and if life is everywhere, waiting in the rocks and clouds, then where is everyone? This is the shadow that hangs over panspermia. If the galaxy is a garden, why is it so quiet? If the seeds are blowing in the wind, why do we not hear the radio signals of the flowers that bloomed? This is the Fermi Paradox, and panspermia makes it worse. If life is difficult to start, if it requires a miracle on Earth, then the silence makes sense. We are alone because we are lucky. But if panspermia is true, then life is easy. It is raining down on every planet. It should be everywhere. And if biology is common, civilization should be common. The fact that we see no one, hear no one, suggests something chilling. It suggests that while life might be common, survival is not. It suggests there is a great filter, a barrier that stops life from becoming spacefaring civilizations. Maybe the filter is multicellularity. Maybe the universe is full of slime, but nothing ever evolves a brain. Maybe the filter is technology. Maybe civilizations destroy themselves as soon as they discover the atom dot, or maybe the filter is the journey itself. Maybe panspermia is a tragedy. Maybe millions of worlds are seeded, but the seeds land on barren sand, or ice, or gas giants. Maybe the universe is full of lonely sparks that flicker for a moment and go out, never finding a neighbor. As we drift toward the end of our journey tonight, we are left with a feeling of profound connection, but also profound isolation. We have learned that we are not separate from the universe. The iron in your blood was forged in a dying star. The water in your cells was delivered by comets. The carbon that makes your shape was drifting in the interstellar smog. And the very spark of life, the first template of a molecule that could copy itself, may have fallen as a microscopic refugee from a sky on fire. We are the universe waking up to itself. We are the way the cosmos tells its own story. Whether we were born here in the mud of a volcanic vent, or whether we arrived in the frozen heart of a meteorite, the truth remains the same. We are made of the same stuff as the stars. We are, in the most literal sense, children of the sky. So the next time you step outside at night, do not look at the stars as distant, cold fires. Look at them as ancestors. Look at the space between them not as a wall, but as a wind that has carried dust and stone, and perhaps the seeds of life, across the dark water of eternity to find a shore called Earth. And in that silence, you might find a strange comfort. We are not alone. We are just part of a very large, very old, and very patient garden. Good night. If meteorites are the stone tablets of the solar system, recording history in hard, dry mineral lines, then comets are the rain that washes the story into being. They are the dirty snowballs of the cosmos, ghosts made of ice and ancient dust that haunt the outer edges of our star's domain. And if we are looking for the true source of life's mobility, we might find that rock is too heavy, but ice is the perfect vessel. To understand why comets matter so much to the theory of panspermia, we have to look at the Earth itself and ask a question that is so simple we often forget to ask it. Where did the water come from? When the Earth formed 4.5 billion years ago, it was not the blue marble we see today. It was a ball of molten magma, a hellscape of volcanoes and colliding tectonic plates. The surface temperature was thousands of degrees. Any water that was present in the original cloud of dust that formed the Earth would have boiled away instantly, lost to the vacuum of space. The Earth was born dry. It was a parched, sterile rock spinning in the dark. Yet, look at it now. 70% of the surface is covered in deep, blue oceans. There is water in the air, water in the ground, water in your cells. If the Earth was born dry, then the oceans had to be delivered. They had to arrive from somewhere else, after the planet had cooled down enough to hold them. This is where the comets come in. Far beyond the orbit of Pluto, in the freezing darkness where the sun is nothing more than a particularly bright star, lies the Oort cloud. This is a spherical shell of billions, perhaps trillions, of icy bodies. They are the leftovers of the solar system's creation, the scraps of ice and dust that were kicked out by the gravity of Jupiter and Saturn. They float there in the deep freeze, preserving the chemistry of the early universe perfectly. Every now and then, a passing star or a galactic tide nudges one of these ice mountains. It begins a long, slow fall toward the sun. As it crosses the frost line, the heat begins to wake it up. The ice sublimates, turning directly from solid to gas, and creates a glowing atmosphere called a coma, and a tail that stretches for millions of kilometers that we believe that about 3.9 billion years ago, during a period called the Late Heavy Bombardment, the inner solar system was pummeled by a storm of these comets. They rained down on the young Earth, smashing into the surface, vaporizing on impact, and releasing their cargo. That cargo was water. The oceans you swim in, the rain that falls on your roof, is literally melted comet ice. But did they bring something else? For decades, scientists speculated that comets might be rich in organic molecules. Since they formed in the cold, dark outer regions, they might have trapped the complex carbon chemistry of the ancient nebula. If meteorites like Murchison carried amino acids, surely comets, which are even more pristine, would carry them too. But speculation is not science. To know for sure, we had to catch one. This brings us to one of the most daring missions in the history of spaceflight, the Rosetta mission. In 2004, the European Space Agency launched a probe to chase down a comet named 67P/Churyumov-Gerasimenko. It took 10 years of slingshotting around planets to catch up to the target. When Rosetta finally arrived in 2014, it revealed a world that looked like a nightmare. Comet 67P was not a smooth snowball. It was a jagged, double-lobed shape that looked like a rubber duck, covered in cliffs, pits, and boulders. It was pitch black, darker than coal, absorbing almost all the sunlight that hit it. And it was singing. The sensors on Rosetta picked up a magnetic song, a strange oscillation in the comet's environment. But the real drama happened when Rosetta released a small lander named Philae. It was supposed to harpoon itself to the surface, but the harpoons failed. Philae bounced. It bounced across the alien surface, floating in the terrifyingly low gravity, before finally settling in the shadow of a cliff. It was a precarious landing. But Philae and Rosetta managed to do their job. They sniffed the gas coming off the comet. They analyzed the dust. And the results were a triumph for the Panspermia hypothesis. Rosetta found glycine. There it was again, the simplest amino acid, the backbone of proteins, floating in the haze of a comet. But it found more. It found phosphorus. Phosphorus is a critical element for life on Earth. It forms the backbone of the DNA double helix and the energy molecule ATP that powers your cells. Without phosphorus, there is no genetic code. And here it was, abundant in the ice of a comet. Rosetta also found a rich crust of organic tars covering the comet. The darkness of the comet wasn't mineral. It was chemical. It was a thick layer of complex hydrocarbons. This discovery reshapes our understanding of an impact. When a comet hits a planet, it doesn't just deliver water. It delivers a prebiotic soup. Imagine a comet crashing into a sterile ocean. The energy of the impact drives chemical reactions. The water provides the solvent. The comet provides the amino acids, the phosphorus, the carbon, and the energy. It is an instant recipe for life. But there is a version of the comet theory that is even more radical. It suggests that the comet doesn't just deliver the ingredients, it delivers the chef. Consider the interior of a comet. As it swings close to the sun, the surface boils, but the heat also slowly seeps into the core. Models suggest that beneath the insulating crust of rock and tar, there could be pockets of liquid water, tiny, temporary lakes trapped inside the ice. These lakes would be warm. They would be rich in organics. They would be shielded from UV radiation by the miles of crust above them. They would be perfect incubators. Some astrobiologists ask, what if life begins inside the comet? What if, during the thousands of years it takes to loop around the sun, the chemistry in those dark, warm pockets crosses the threshold into biology? If this is true, then comets are not just delivery trucks. They are mobile homes. They are incubators traveling through the void. When they strike a planet, they crack open like an egg, releasing not just the potential for life, but life itself. This idea, cometary panspermia, solves one of the biggest problems with the Earth-based origin of life, time. Life appears on Earth almost as soon as the planet cools down. It appears so quickly that some scientists feel it is uncomfortably fast. Evolution usually takes time. But if life was already cooking in the comets for millions of years before they arrived, then Earth didn't have to start from scratch. It just had to provide the home. However, comets are part of our solar system. They are local. Even if they come from the Oort cloud, they are still bound by the gravity of our sun. To truly embrace the cosmic scale of panspermia, we have to look beyond the sun's domain. We have to look at the vast, terrifying emptiness between the stars. We call it the interstellar medium. And for a long time, we thought it was truly empty, a vacuum more perfect than anything we can create in a lab. But as our telescopes got better, and specifically as we learned to look at the universe not just in visible light, but in radio waves and infrared, we realized that the emptiness is an illusion. The space between the stars is filled with smoke. Huge, billowing clouds of gas and dust stretch for light years across the galaxy. These are the molecular clouds. They are the nurseries where new stars are born, but they are also the graveyards where old stars die and scatter their ashes. When we analyze the light passing through these clouds, we see absorption lines. Every molecule absorbs light at a specific frequency, leaving a fingerprint in the spectrum. By reading these fingerprints, we can tell exactly what the clouds are made of. We expected to find hydrogen, maybe some helium, simple stuff. Instead, we found a distillery in the vast cloud known as Sagittarius B2. Near the center of our galaxy, astronomers found billions of liters of alcohol, specifically ethanol and methanol. We found simple sugars, glycolaldehyde. We found water. We found ammonia. We found Buckminster fullerenes, buckyballs, complex cages of 60 carbon atoms shaped like soccer balls. We found polycyclic aromatic hydrocarbons, PAHs, which are ring-shaped molecules that look suspiciously like the skeletal structures of cholesterol and sex hormones. The interstellar medium is not empty. It is a thick, toxic organic smog. This discovery led to one of the most controversial and fascinating chapters in the history of panspermia, driven by two men who were not afraid to be called heretics, Sir Fred Hoyle and Chandra Wickramasinghe. Fred Hoyle was a giant of astronomy. He coined the term Big Bang, ironically to mock a theory he disagreed with, and figured out how stars fuse elements. Chandra Wickramasinghe was his student and collaborator. In the 1970s, they began to study the nature of interstellar dust. They looked at how the dust in the galaxy absorbed and scattered light. They tried to match that data with various materials in the lab. They tried graphite. They tried silicates. They tried ice. Nothing fit the data perfectly. Then, out of curiosity, they tried cellulose, the stuff plants are made of. Fit better. They tried dried bacteria. Specifically, E. coli bacteria that had been desiccated, dried out. The match was nearly perfect. Hoyle and Wickramasinghe looked at the data and made a leap that terrified the scientific community. They proposed that the dust grains floating in the interstellar clouds were not just dust. They proposed that they were freeze-dried bacteria. They argued that the entire galaxy is a single, connected biological system. They suggested that life forms in the atmospheres of cool stars or in the tails of comets gets ejected into the interstellar medium and then replicates in the molecular clouds using the energy of starlight. To them, the molecular clouds were not just chemical fogs. They were living colonies on a scale we can barely comprehend. According to their living dust theory, planets like Earth are simply places where this cosmic life gets swept up and thrives. They even went so far as to suggest that new diseases, flu pandemics, for instance, might be caused by the Earth passing through a stream of cometary dust carrying new viruses from space. This was and remains a fringe theory. The idea that the flu comes from space is almost certainly wrong. We can trace the evolution of viruses perfectly well on Earth. And most astronomers believe that the bacterial match in the light spectrum can be explained by complex polymers that aren't actually alive. But Hoyle and Wickramasinghe were right about the chemistry. They were right that the universe is soaked in the building blocks of biology. Even if the dust isn't alive, it is prebiotic. It means that every new star system that forms is born in a cloud of sugar, alcohol, and amino acids. This changes the odds of life emerging elsewhere. If every solar system starts with a starter kit of organic molecules, then life doesn't have to be a 1 in a trillion miracle of chemistry. It just has to be the inevitable result of that chemistry falling onto a wet planet. It implies that the universe is trying to make life. It is not indifferent. The laws of physics and chemistry seem stacked in favor of biology. The carbon atom loves to bond. The water molecule loves to dissolve. The dust clouds love to protect. As we gaze into these clouds, into the Orion Nebula or the pillars of creation, we are looking at the waiting room of existence. Those dark, opaque knots of gas are protecting delicate molecules from the harsh radiation of the galaxy, nurturing them until gravity pulls them together to form a star, a planet, and perhaps, eventually, an eye to look back at the cloud. But if the clouds are the factory and the comets are the delivery trucks, there is still one piece of the puzzle missing. We need to know if packages are being delivered between the stars right now. We need to know if a rock from a distant alien sun can actually cross the abyss and enter our solar system. For centuries, this was pure mathematics. We assumed the distances were too great. We assumed that solar systems were isolated islands, separated by oceans of nothingness that no rock could cross. Then, in the year 2017, a telescope in Hawaii saw something that shouldn't be there. It was a rock. It was moving too fast. And it was not orbiting our sun. It was a visitor. The arrival of Oumuamua changed the conversation from "could it happen?" to "it is happening." And it forced us to ask, if a rock can travel from one star to another, can it bring a passenger? The story of Oumuamua is not just about an asteroid. It is about the realization that the galaxy is a blizzard of rocks. If we saw one, it means there are trillions we don't see. And if there are trillions of rocks flying between the stars, then the galaxy is not a collection of lonely islands. It is an archipelago connected by a constant, invisible exchange of matter. But Oumuamua was dry. It was a stone. What we really needed was a visitor that carried the magic ingredient: ice. And 2 years later, we got exactly that. As we prepare to examine these interstellar visitors, we must hold in our minds the sheer scale of what this implies. We are moving from a view of life as a local accident to a view of life as a galactic imperative. If the clouds are full of seeds, and the comets are full of water, and the rocks are flying between the stars, then the sky is not a ceiling. It is a door, and it is wide open. Now, we must turn our attention to these visitors. Who are they? Where did they come from? And most importantly, could we ever catch one and open it up to see if anything is sleeping inside? Because if we found a single microbe in a rock from another star, the silence of the universe would end. We would know, finally, that we are part of a cosmic community. But until we catch one, we have to look at the messengers that have already landed. We have to look at the dust in our own museums and the strange, unexplained anomalies in the history of life on Earth itself. Could it be that the aliens have already arrived? Could it be that the invasion happened 540 million years ago? Let's explore the idea that our own evolution has been driven not just by mutation, but by infection from above. The theory of viral panspermia awaits. The story of Oumuamua is the story of a door opening. For centuries, our model of the solar system was like a clockwork mechanism sealed inside a glass case. We knew the planets orbited the sun. We knew the asteroids orbited the sun. We knew the comets, even the distant ones in the Oort cloud, were bound to the sun by gravity. We assumed that while the galaxy was full of stars, the space between them was an impassable ocean, and solar systems were lonely islands that never exchanged a single pebble. But on October 19, 2017, the glass case shattered. The object was spotted by the Pan-STARRS telescope in Hawaii, a system designed to hunt for near-Earth objects that might pose a threat to our planet. Usually, these objects are roundish asteroids moving at predictable speeds. But this one was different. It was screaming through the solar system at 87 kilometers per second, a speed so high that the sun's gravity could not hold it. It wasn't orbiting. It was passing through. We named it Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. And it was, in every sense, a messenger. It brought us the news that we are not isolated. As astronomers swung every available telescope toward this fleeing visitor, the mystery deepened. Oumuamua didn't look like a normal rock. As it tumbled through the dark, its brightness pulsed rhythmically, suggesting a shape that was incredibly elongated, like a cigar, or perhaps a flattened pancake, hundreds of meters long but very thin. We had never seen an asteroid with that geometry before. Then, it did something even stranger. As it moved away from the sun, it accelerated. Not much, but just enough to defy the laws of pure gravity. It was being pushed. For a brief electric moment, the world wondered if it was a ship. The acceleration could have been the result of a solar sail catching the light. The SETI Institute's search for extraterrestrial intelligence turned its radio dishes toward the object, listening for a beep, a hum, a sequence of prime numbers. Anything that sounded like a machine. The silence was absolute. There were no radio signals. The push was likely natural. The object was probably venting gas, acting like a weak rocket, even though we couldn't see the tail. But even if Oumuamua was just a rock, its significance for panspermia is monumental. Before 2017, we thought interstellar transfer was theoretically possible but practically impossible. Oumuamua proved that rocks from other stars pass through our system. And if we saw one after only a few years of looking with sensitive telescopes, statistical models imply that there must be trillions of these objects drifting through the Milky Way at any given moment. The galaxy is not empty space. It is a blizzard of rogue stones. If Oumuamua was the dry, rocky messenger, the second visitor was the wet one. In 2019, an amateur astronomer named Gennady Borisov spotted another intruder. This 1-2I/Borisov was unmistakably a comet. It had a tail. It was spewing gas and dust. Borisov was the proof of concept for galactic panspermia. Here was a chunk of ice that had formed around a distant, alien star, perhaps billions of years ago. It had been ejected from its home, traveled across the unimaginable light years of the void, and entered our solar system still carrying its cargo of water and organic chemicals. If it had collided with Earth, it would have delivered a sample of an alien nebula to our oceans. These visitors force us to reimagine the galaxy. We used to think of life as a local chemistry experiment. Now, we have to think of it as a potential contagion. If life evolves on a planet and that planet gets hit by an asteroid, the debris enters the galactic current. Rocks carrying microbes act like seeds caught in a cosmic wind. Most will fall on barren ground, into stars or gas giants or cold vacuum, but some inevitably will find a new home. This implies that if we ever find life on a planet around Alpha Centauri or TRAPPIST-1, it might not be truly alien. It might be our cousin. We might all be part of a single, sprawling family tree that has been branching out across the spiral arms of the Milky Way for 10 billion years. But while we watched Oumuamua and Borisov leave, humanity decided it was done waiting. We were no longer content to let the universe drop samples on our doorstep. We wanted to go out and grab them ourselves. We entered the era of sample return. This is a shift in human history as profound as the first tool or the first fire. Instead of interpreting the blurry light in a telescope, we built robot explorers, Hayabusa 2 from Japan and OSIRIS-RX from the United States, and sent them to hunt asteroids. Their targets were Ryugu and Bennu, two rubble pile asteroids that are essentially fossils from the dawn of the solar system. These aren't solid rocks. They are loose collections of gravel and boulders held together by weak gravity. They are time capsules that haven't changed in 4.5 billion years. The missions were harrowing. Hayabusa 2 had to bomb Ryugu to create a crater, then touch down gently to collect the subsurface dust. OSIRIS-RX had to high-five Bennu, blasting it with nitrogen gas to stir up the surface and trapping the debris in a collector. When these samples returned to Earth, Hayabusa 2 landing in the Australian outback in 2020, and OSIRIS-RX dropping its canister into the Utah desert in 2023, scientists finally had what they had dreamed of for a century: pristine, unburned, uncontaminated space dirt. They didn't have to worry about the heat of re-entry destroying delicate molecules. They didn't have to worry about Earth bacteria crawling into the cracks. These grains were sealed in the vacuum of space until they reached the clean room, and what they found inside these grains vindicated the boldest predictions of astrochemistry. Inside the samples from Ryugu, scientists found uracil. Uracil is not just a random carbon chain. It is one of the 4 nucleobases of RNA. It is a letter in the genetic code. Along with it, they found vitamin B3, niacin, and a host of other prebiotic organics. Think about that. We flew a robot hundreds of millions of miles to a rock that has looked exactly the same since before the Earth existed. We brought a teaspoon of it back, and inside, we found the letters of our own genetic alphabet. This discovery moves panspermia from a hypothesis of possibility to a hypothesis of inevitability. The question is no longer, can the ingredients of life survive in space? The question is there anywhere in space that doesn't have the ingredients of life? It seems the universe is wired for biology. It creates the parts, freezes them in asteroids, and flings them around like a farmer sowing seeds. The hardware of life is everywhere. The software, the spark that turns chemistry into biology, is the only mystery left. But there is a shadow version of this story, a version that moves away from the blind, accidental drifting of rocks and looks at the possibility of intention. What if the seed didn't fall? What if it was thrown? This is the hypothesis of directed panspermia. It is a controversial, uncomfortable, and deeply fascinating idea proposed by two of the greatest minds in 20th century biology, Francis Crick and Leslie Orgel. Francis Crick is famous for co-discovering the double helix structure of DNA. He understood the code of life better than almost anyone. And as he looked at it, at the universality of the genetic code, where every organism from a bacteria to a blue whale reads the same language, he felt a sense of unease. If life evolved here on Earth from a messy, chaotic, primordial soup, shouldn't there be variety? Shouldn't there be different versions of the genetic code, different operating systems competing with each other? Why was there only one, and why did it appear so suddenly and so perfectly formed in the fossil record? Crick also pointed to oddities in our biochemistry. For example, the element molybdenum is crucial for many enzymes in our bodies, yet it is quite rare on Earth. Why would life depend so heavily on a metal that is hard to find? In 1973, Crick and Orgel published a paper suggesting a radical solution. They proposed that life may have been deliberately sent here by an advanced civilization. Imagine a society facing the death of their star. They know they cannot evacuate their entire population. The distances are too great. The energy requirements for moving billions of people are impossible. But they want their heritage to survive. They want to preserve the spark of life. So they build a fleet of small, automated probes. They don't send colonists. They send packages. They load these probes with hardy bacteria, algae, or perhaps a custom-designed starter organism that carries the genetic code of their biosphere. They launch these seeds in all directions, targeting young star systems where planets are just beginning to cool. They aim for the Goldilocks zones. The probes travel for thousands of years, silent and unpowered. When they reach a target planet, they crash into the ocean. The capsule dissolves. The bacteria are released. They multiply, filling the seas, pumping oxygen into the atmosphere, and beginning the long, slow climb of evolution. According to this theory, we are not the result of a lucky lightning strike in a warm pond. We are a colony. We are the project of a ghost civilization that lived and died billions of years ago. Crick himself later softened his stance, admitting that the RNA world hypothesis explained the origin of life better than aliens. But the idea of directed panspermia hasn't gone away. In fact, it has become more relevant than ever because we are starting to think about doing it. We are currently standing on the threshold of becoming the ancient aliens. Projects like Breakthrough Starshot are designing tiny, laser-propelled sails that could reach Alpha Centauri in our lifetimes. These probes will be small grams, not tons. We couldn't send a human, but we could send DNA. We could send Deinococcus. We could send tardigrades. This raises a profound ethical question, one that haunts the field of astrobiology. Do we have the right to seed the universe? If we find a planet that is habitable but sterile, a world with water and sunlight but no life, is it our duty to bring it to life? To play gardener to the galaxy? Or would that be an act of cosmic vandalism, destroying the pristine beauty of a dead world? And what if the planet isn't sterile? What if it has its own fragile, simple life starting to evolve? If we drop our hardy, battle-hardened Earth bacteria there, we might wipe out the natives. We would be an invasive species on a planetary scale. This is the problem of forward contamination, and NASA takes it very seriously. We scrub our rovers with alcohol and heat them to kill every last microbe before launch. We crashed the Cassini spacecraft into Saturn to avoid accidentally contaminating the moons Enceladus or Titan. We are terrified of accidentally becoming the Panspermia event that destroys an alien ecosystem. But if we survive for another 1,000 years or 1,000,000, will we still be so careful? Or will we see the dead galaxy as a canvas waiting to be painted green? Directed Panspermia shifts the narrative from luck to agency. It suggests that intelligence itself is a reproductive mechanism for the universe. Civilization is not just a way to build cities. It is a way for life to jump the gap between stars. But whether the seed was sent by a rocket or carried by a rock, it still needs a place to land, needs a home. And this brings us to the geography of the galaxy. Not all stars are created equal. Not all neighborhoods in the Milky Way are safe. If we want to understand where life comes from, we have to understand the galactic habitable zone. Just as there is a safe distance from a star where water is liquid, there is a safe distance from the center of the galaxy where life can survive. Too close to the center and the density of stars is too high. Supernovas go off constantly, sterilizing planets with gamma rays. Gravity from passing stars disrupts planetary orbits, flinging worlds into the dark. It is a chaotic, violent downtown where life barely stands a chance. Too far out on the rim, and the galaxy is too poor. There aren't enough heavy elements, iron, silicon, carbon, to build rocky planets or complex molecules. The stars are lonely, metal-poor things surrounded by gas. We live in the suburbs. The Orion Spur. It is a quiet, boring part of the galaxy, rich enough in metals to build Earth, but far enough from the violence of the core to remain stable for billions of years. But there is another environment, one we rarely think about, that might be the perfect engine for panspermia. Globular clusters. These are tight, spherical swarms of ancient stars. In a globular cluster, stars are packed together tightly, sometimes light weeks apart rather than light years. A civilization on a planet in a globular cluster wouldn't see a night sky. They would see a sky blazing with thousands of suns. In such a dense environment, panspermia would be inevitable. If a rock was knocked off one planet, it would almost certainly hit another star system within a few years. Life could spread like a wildfire, jumping from star to star until the whole cluster was alive. Some scientists wonder if we should be listening to these clusters. If there is a galactic club, a network of connected civilizations, that is where they would be. But so far, the clusters are silent. The galaxy is silent. And this silence brings us back to the great tension at the heart of our story. We have seen that the chemistry of life is everywhere. We have seen that the vehicle, rocks, comets, dust, is reliable. We have seen that life is tough enough to survive the trip. So where is everyone? This is the Fermi Paradox. If panspermia is true, the universe should be teeming with life. It should be noisy. It should be crowded. Instead, we look out and see only fire and stone. This silence suggests a dark possibility. It suggests that while the seed is common, the flower is rare. Perhaps the universe is full of bacteria, buried deep in the rocks of Mars, floating in the clouds of Jupiter, swimming in the oceans of Enceladus. Perhaps the galaxy is full of slime, but complexity, intelligence, maybe that is the hard part. Or maybe there is a filter, a great filter. This concept suggests that there is a step in the evolution of life that is almost impossible to cross. Maybe it's the jump from single cells to multicellular animals. It took Earth 3 billion years to figure that out. Maybe most planets never get past the bacteria stage. They stay as slime worlds until their suns die. Or maybe the filter is civilization itself. Maybe as soon as a species gets smart enough to build rockets and split atoms, it destroys itself. If panspermia is real, it means the first step, the origin of life, is easy. It means the great filter is not behind us. It might be ahead of us. But there is one more twist to the panspermia story, one that brings the alien invasion right into our own DNA. It is a theory that sounds like a fever dream, but it has evidence hidden in the human genome. We tend to think of evolution as a slow, steady tree, branching out over time. Darwin's tree. But what if the tree was grafted? What if new genetic information didn't just evolve from the bottom up, but fell from the sky? This is the theory of viral panspermia. Viruses are strange things. They are not quite alive, but they carry genetic code. They are essentially information packets. On Earth, viruses are the drivers of evolution. They insert their genes into hosts, sometimes leaving those genes behind. A significant chunk of the human genome, perhaps as much as 8%, is made of broken, ancient viruses that infected our ancestors millions of years ago. Some proponents of panspermia ask, what if those viruses didn't originate here? What if the Earth travels through a cloud of cosmic dust, and that dust carries a rain of viruses? These viruses wouldn't necessarily make us sick. Instead, they might insert new genetic instructions into the biosphere. Imagine the Cambrian explosion, that sudden moment 540 million years ago when life on Earth went from simple worms and sponges to a wild explosion of complex eyes, legs, shells, and skeletons. It happened so fast that Darwin himself worried it broke his theory. Could it be that the Earth passed through a viral cloud? Did a package of upgrade software rain down from the sky, inserting the code for complex eyes or hard shells into the simple creatures of the ancient ocean? It is a wild speculation. It borders on science fiction, but it highlights how little we know about the influence of the cosmos on our biology. We are an open system. We are constantly bathed in the wind of the universe. As we near the end of our reflection on panspermia, we are left not with a conclusion, but with a change in perspective. We usually define alien as something foreign, something other. But if panspermia is true, then the word loses its meaning. If the water in your cup is from a comet and the carbon in your breath is from a star, and the very seed of life drifted here from a distant world, then who is the alien? We are the travelers. We are the awakening of the interstellar dust. We are the way the universe has found to look in the mirror. The boundaries between Earth and space are imaginary lines drawn by gravity and atmosphere. In reality, there is no separation. The wind that blows between the stars blows through you. So, tonight, as you drift towards sleep, think of the rock that fell in Murchison. Think of the dark, warm water inside a comet. Think of the ancient, rusted surface of Mars. You are connected to all of them. You are not just a creature of the Earth. You are a citizen of the Milky Way. If you enjoyed this journey through the deep history of life and the cosmos, please consider liking the video and subscribing to Mysteries Beneath Earth. We are a small channel, and every subscriber helps us keep these bedtime documentaries going. Thank you for listening. And as always, keep looking up. The story is written in the stars, and we are just beginning to learn how to read it. For the vast majority of human history, and indeed for the entirety of geological history as far as we understood it, the solar system was considered a closed room. We imagined the sun as a lonely hearthfire in a vast, dark wilderness. The planets, the asteroids, and the comets were the family gathered around that fire, bound to it by the invisible, unbreakable chain of gravity. We assumed that while we could look out the windows at the distant stars, nothing ever came in from the cold. The space between solar systems was thought to be so impossibly wide that it acted as a quarantine zone. A rock from another star crossing the abyss to visit ours was mathematically dismissed as an event so rare it might as well be impossible. But in October of 2017, the door to that closed room was kicked open. It began as a flicker in the data stream of the Pan-STARRS telescope in Hawaii. This instrument scans the sky every night, hunting for near-Earth objects, asteroids that might threaten our planet. Its software is written to look for things that move in circles, objects that trace the familiar elliptical paths of things orbiting our sun. But the object that triggered the alert on that autumn night was not moving in a circle. It was moving in a hyperbola, an open-ended curve that has only one meaning in orbital mechanics: escape. This object was traveling at 87 kilometers per second. To put that in perspective, a rifle bullet travels at about 1 kilometer per second. This rock was moving so fast that the sun's massive gravity was just a speed bump. It wasn't falling into an orbit. It was passing through. It had come from the deep, uncharted darkness of interstellar space, dived toward our sun, and was now hurtling back out into the void, never to return. We named it Oumuamua. In the Hawaiian language, the name reflects the profound nature of the event. A messenger from afar arriving first. It was the first confirmed interstellar object humanity had ever seen. If Panspermia suggests that life can hop from star to star, Oumuamua was the proof of the vehicle. But as astronomers trained every available telescope on this fleeing visitor, the mystery of what it actually was began to deepen. It didn't behave like the asteroids we know. As it tumbled through the vacuum, its brightness pulsed dramatically, dimming and brightening every few hours. This light curve suggested a shape that defied all previous experience. It wasn't a potato-shaped lump like most asteroids. It was extremely elongated, perhaps 10 times longer than it was wide. Some models pictured it as a cigar, others as a flattened pancake. This geometry is bizarre for a natural object. In space, gravity and collisions tend to make things round. To have something so stretched out suggested a violent origin. Perhaps it was a shard of a planet torn apart by the tidal forces of a dying star, or a fragment of a crust ejected during a supernova. Then came the anomaly that truly unsettled the scientific community. As Oumuamua moved away from the sun, it accelerated. It wasn't a massive push, but it was statistically significant. Newtonian physics says a rock should slow down as it fights the sun's gravity on its way out. Oumuamua sped up. Comets do this. When a comet heats up, ice turns to gas, shooting out jets that act like tiny thrusters. But Oumuamua had no tail. There was no cloud of gas, no dust, no visible coma. It was dry and dark. So what was pushing it? For a brief, electric moment, the silence of the scientific journals was broken by a whisper of the extraordinary. Could it be artificial? Could the acceleration be due to light pressure on a solar sail? Was Oumuamua not a rock, but a probe? The Breakthrough Listen project, dedicated to finding alien intelligence, turned its massive radio dishes toward the object. They listened for hours across billions of radio channels, hoping to catch a ping, a telemetry stream, a navigational beacon. The silence was absolute. Oumuamua was quiet. It was almost certainly a natural object, perhaps a nitrogen iceberg or a rock with invisible outgassing. But its identity as a rock makes it arguably more important for panspermia than if it were a spaceship. A spaceship is a singular invention. A rock is a statistic. If we detected one interstellar object after only a few years of having telescopes sensitive enough to see it, that implies something staggering about the density of the galaxy. It suggests that Oumuamua was not a freak accident. It suggests that at any given moment, there are likely thousands of these interstellar wanderers passing through our solar system, and trillions upon trillions of them drifting through the Milky Way. Think of what this means for the spread of life. We used to think the galaxy was an archipelago of isolated islands. Oumuamua taught us that it is a blizzard. The galaxy is churning with material. Every time a star system forms, it ejects billions of rocks. Every time a planet is struck by a giant asteroid, it bleeds debris into the interstellar current. That if even a tiny fraction of these rocks carry microbial spores, encased in the protective arc of rock we discussed earlier, then the galaxy is not separated by voids. It is connected by a circulatory system. Oumuamua showed us that the blood cells of the galaxy are constantly flowing through our own veins. And it wasn't long before the second messenger arrived. Just 2 years later, in 2019, an amateur astronomer named Gennady Borisov spotted another intruder. This one, named 2I/Borisov, was different. It wasn't a dry, confusing rock. It was a comet. Unmistakable, beautiful, and volatile. It had a tail. It was spewing gas and dust. And as we analyzed the light reflecting off that gas, we realized something profound. It looked exactly like our comets. It was made of water ice, carbon monoxide, and dust. It proved that the chemistry of a distant alien star system, the place where Borisov was born, was identical to the chemistry of our own solar system. Borisov was the wet carrier. If Oumuamua was the hull of the ship, Borisov was the cargo hold. Carried water, the solvent of life. Carried organics. If it had collided with the primitive Earth, it would have delivered a sample of an alien nebula directly into our oceans. These two visitors changed the psychological landscape of science. We no longer look at the stars and wonder if anything can cross the gap. We know they cross the gap. The question shifted from, is it possible? To what is inside them? But humanity is an impatient species. We are not content to sit on our planet, waiting for the universe to throw rocks at us so we can pick through the rubble. We want to see the source. We want to touch the dust before it burns up in our atmosphere. And so, while the interstellar visitors were passing through, we launched our own ships to intercept the asteroids of our own system. This brings us to the era of sample return, a technological leap that has turned astrobiology from a science of speculation into a science of touch. For decades, we analyzed meteorites that fell to Earth. But meteorites are compromised witnesses. They have suffered the violence of atmospheric entry, heating up to thousands of degrees. They have laid in the mud or the ice, absorbing terrestrial bacteria and water. A skeptic can always say that amino acid didn't come from space. It came from the soil where the rock landed. To silence the skeptics, we had to go to the mountain. We had to fly a robot to an asteroid, grab a handful of dirt that had been vacuum sealed since the dawn of time, and bring it home. The Japanese space agency, JAXA, led the way with the Hayabusa 2 mission. Its target was Ryugu, a diamond-shaped asteroid that is not a solid rock, but a rubble pile, a loose collection of gravel held together by gravity. Ryugu is a C-type asteroid, a carbon-rich relic from the early solar system. The mission was a display of precision that borders on the magical. The spacecraft didn't just orbit. It descended and touched the surface. It fired a small tantalum bullet into the asteroid to kick up dust, which it then caught in a horn. But that wasn't enough. Hayabusa 2 wanted a sample from deep inside the rock, protected from the solar wind. So it deployed a small carry-on impactor, essentially a copper bomb. It blasted a crater into the asteroid, waited for the dust to clear, and then descended again to scoop up the subsurface material. When the return capsule streaked through the night sky over the Australian outback in December 2020, it carried a treasure more valuable than gold. It carried 5 grams of black, sandy dust. Almost simultaneously, NASA was conducting a similar mission called OSIRIS-RX. Its target was Bennu, another carbon-rich rubble pile that has a small chance of hitting Earth in the distant future. The sample collection was dramatic. The spacecraft's arm sank 0.5 meter into the soft surface of the asteroid, firing a burst of nitrogen gas to stir up a massive cloud of debris. It grabbed so much material, hundreds of grams, that the container lid couldn't close properly at first, leaking dust into space like an overfilled suitcase. When these samples arrived in the sterile clean rooms of Japan and the United States, scientists began to disassemble them atom by atom. These grains had never touched an atmosphere. They had never been heated by re-entry. They were the raw, frozen truth of the universe. And what they found inside bridged the gap between the dead stone and the living cell. Inside the black dust of Ryugu, scientists found uracil. Uracil is not a generic organic molecule. It is a nucleobase. Specifically, it is one of the 4 letters of RNA. Along with adenine, guanine, and cytosine, uracil is the code used by life to transmit genetic instructions. RNA is thought to be the precursor to DNA, the original molecule of life on Earth. And here was one of its key components, sitting in a rock that formed millions of years before the Earth existed. They also found vitamin B3, niacin, a critical cofactor for metabolism. They found a vast library of amino acids. They found organic molecules that form structures called micelles, tiny bubbles that can act like primitive cell membranes. The Ryugu and Bennu samples proved that asteroids are not just rocks. They are chemical kits. They contain the hardware for genetics, uracil, the hardware for metabolism, vitamins, and the hardware for containment membranes. This discovery forces us to reconsider the primordial soup theory. We used to think that Earth's oceans were the kitchen where simple chemicals slowly cooked into complex ones over millions of years. But the asteroids suggest that the soup was pre-cooked in space. The Earth didn't have to invent uracil. It didn't have to invent membranes. They were delivered, ready-made, by the trillions of tons during the heavy bombardment. It transforms our view of the early Earth from a lonely laboratory into a grand assembly floor. The parts were manufactured in the molecular clouds, stored in the deep freeze of the asteroids, and delivered by gravity. Life, it seems, is a Lego set that the universe dumps onto every wet planet it can find. But this leads to a shift in our thinking. If the ingredients are everywhere, and the delivery systems are constant, then the origin of life becomes less of a miracle and more of a mechanism. And if it is a mechanism, could it be engineered? This brings us to the most controversial, the most unsettling, and perhaps the most profound variation of the panspermia hypothesis. We have talked about accidental panspermia, rocks and comets wandering blindly. Now we must talk about intent. What if the seed didn't fall? What if it was thrown? This is the hypothesis of directed panspermia. It moves the agency from gravity to intelligence. It asks us to consider whether the sudden appearance of life on Earth 3.8 billion years ago was not a chemical accident, but a colonization event. The primary architect of this idea was not a fringe conspiracy theorist, but a Nobel Prize winner, Francis Crick. Crick, along with James Watson, unraveled the double helix structure of DNA. He stared deeper into the code of life than almost any human being before him. And what he saw there disturbed him, that he was struck by the uniformity of life. Every organism on Earth, from the bacteria in a hydrothermal vent to the eagle soaring above it, uses the exact same genetic code. The same three-letter codons translate into the same amino acids. If life had evolved from a messy, competitive soup on Earth, Crick argued, shouldn't we see different codes? Shouldn't there be shadow biospheres, lineages that used a different molecular language? Why was there only one winner, and why did it appear so suddenly? The oldest fossils appear almost immediately after the Earth becomes cool enough to support them. It seemed to Crick that life didn't undergo a long, slow evolution from simple chemistry. It seemed like it arrived fully formed at in 1973. Crick and the chemist Leslie Orgel published a paper titled Directed Panspermia. In it, they proposed a thought experiment that chills the blood. They suggested that life on Earth might be a shipment. Imagine an advanced civilization somewhere in the galaxy billions of years ago. Perhaps their star was dying. Perhaps they were facing a catastrophic resource collapse. Or perhaps they were simply motivated by the same urge that drives us to plant trees we will never sit under. The desire to leave a legacy. They realize they cannot travel the stars themselves. The energy required to move a population is impossible. Biology is fragile. Radiation is deadly. Time is vast. So instead of sending themselves, they send their biology. They engineer a payload. It is not a ship of colonists, but a ship of microbes. They choose bacteria that are hardy, capable of surviving radiation and freezing. Perhaps they engineer them to be starter organisms, creatures designed to digest rock, produce oxygen, and pave the way for future complexity. They are terraformers. They load these seeds into thousands of small, automated probes. They launch them in all directions, aiming for the habitable zones of nearby stars. They are scattering dandelion seeds into the cosmic wind, hoping one will land on fertile soil. One of those probes, Crick suggested, entered the solar system 4 billion years ago. It splashed down in the sterile, prebiotic ocean of Earth. The casing dissolved. The bacteria spilled out. They looked around at the sunlight and the water, and they began to divide. We are the result. The directed panspermia hypothesis explains the universality of the genetic code. We are all descended from that single shipment. It explains the sudden appearance of life. It explains why some essential elements in our enzymes, like molybdenum, are rare on Earth but common elsewhere in the galaxy. Crick later walked back this theory, admitting that the discovery of the RNA world, the idea that RNA acted as both genetic code and enzyme, solved many of the problems he was worried about. He eventually concluded that life probably did start here. But the idea refuses to die. And ironically, it refuses to die because of us. We are currently becoming the aliens Crick imagined. Right now, in laboratories and space agencies, humans are discussing the ethics of seeding other worlds. We have found planets around other stars, Proxima Centauri b, TRAPPIST-1e. We are building lasers to propel tiny starshot sails to these systems. We are asking, if we find a planet that has water but no life, do we have the right to plant a seed? If we sent a canister of cyanobacteria to a dead world, in 1 billion years it might have a breathable atmosphere. It might have forests. It might have eyes looking up at the stars. We call this planetary protection. When we are trying to avoid it, scrubbing our Mars rovers to prevent contaminating the red planet. But if we accept that Earth will one day be uninhabitable, planetary protection might flip. It might become a moral imperative to spread life before the sun swallows us. This realization creates a strange loop. If we are thinking about doing it, surely others have thought about it. If civilizations are common, the galaxy should be filled with these seeds. This brings us to the geography of the galaxy. If someone is sending seeds, where are they? And where are the gardens? To understand the distribution of life, we have to look at the map of the Milky Way, not just as a collection of stars, but as a habitat. We have to explore the concept of the galactic habitable zone. Just as a solar system has a Goldilocks zone, where the temperature is right for liquid water, the galaxy itself has a sweet spot. If you go too close to the galactic center, the environment is hostile. The density of stars is incredibly high. Supernovas, exploding stars, go off frequently, bathing nearby planets in sterilizing gamma radiation. Giant molecular clouds disrupt planetary orbits. A civilization trying to rise in the galactic core would be constantly reset by cosmic violence. It is a high-energy, high-risk downtown. If you go too far out to the rim, the galaxy is quiet, but it is poor. The stars there are metal poor, meaning they lack the heavy elements like iron, silicon, and oxygen created by previous generations of dying stars. Without these elements, you cannot build rocky planets. You cannot build blood. You cannot build computers. The rim is a lonely wasteland of gas giants and dust. We live in the suburbs, the Orion spur of the Milky Way. We are far enough from the core to avoid the constant radiation storms, but close enough to the star-forming regions to be rich in heavy elements. We are in the prime real estate for panspermia. But there is one environment that defies this map, an environment that might be the ultimate engine for the spread of life: the globular cluster. These are ancient, spherical swarms of stars that orbit the galactic center like satellites. Inside a globular cluster, the stars are packed tight. In our neighborhood, the nearest star is 4 light-years away. In a cluster, stars might be light weeks or even light days apart. Imagine a night sky in a globular cluster. It wouldn't be dark. It would be blazing with thousands of suns, some so bright they cast shadows. In such a dense environment, the transfer of material between stars would be inevitable. If an asteroid hit a planet in a globular cluster, the debris wouldn't drift for millions of years. It would reach the neighboring star in a few years. Panspermia would be rapid and contagious. If life started on one planet in a cluster, It would infect the entire cluster in a geological blink. If directed panspermia is real, a civilization in a cluster wouldn't need high-tech probes. They could almost fire rockets with conventional chemical engines to reach their neighbors. Some astronomers argue that if we want to find the Galactic Club, a network of communicating civilizations, we should look at these clusters. They are the mostly likely places for life to have synchronized and spread. Yet, when we listen to the clusters, we hear silence. When we look at the habitable zone, we see no Dyson spheres. When we analyze the asteroids, we find the parts of life, but not the messages of life. This silence brings us back to the edge of our understanding. We have the mechanism, rocks and comets. We have the ingredients, uracil and amino acids. We have the motive, survival, but we still lack the contact. Perhaps the contact is not something we see with telescopes. Perhaps it is something we see with microscopes. There is one final frontier in the panspermia hypothesis that suggests the alien invasion is not a dramatic landing of a ship, but a subtle, continuous rain of genetic information that has been shaping us for millions of years. This is the theory of viral panspermia. Viruses are the dark matter of biology. They are not technically alive, they cannot reproduce on their own, but they are the most abundant biological entities on Earth, and they are small enough to float. Some researchers, pushing the boundaries of the possible, suggest that viruses might be the true astronauts. They are small enough to be shielded inside dust grains. They are simple enough to survive extreme stasis. What if the evolution of life on Earth is not a closed loop? What if, occasionally, the Earth passes through a stream of cometary dust that is loaded with viral code? We know that viruses can insert their genes into the DNA of their hosts. We carry the scars of these infections in our own genome. Retroviruses have shaped the evolution of the placenta in mammals. They have shaped our immune systems. The radical proposal is that these viruses didn't originate here. They fell from the sky. They acted as upgrade patches for the biosphere. Consider the Cambrian explosion 540 million years ago. In a blink of geological time, life went from simple, soft-bodied worms to a riot of complex armor, eyes, legs, and predators. It was such a sudden increase in complexity that Darwin himself worried it undermined his theory of slow, gradual change. Proponents of viral panspermia ask, did we get an upgrade? Did a cloud of cosmic viral material drift through the atmosphere, infecting the oceans with new genetic subroutines that allowed for the development of complex eyes or hard shells? It sounds like fiction. It is almost certainly not the mainstream view, but it forces us to confront the openness of our world. We are not sealed in a bubble. The atmosphere is a membrane, and membranes are permeable. As we stand here, holding the dust of Ryugu in our hands, staring at the trail of Oumuamua, and mapping the silence of the stars, we are left with a picture of the universe that is radically different from the one our ancestors knew. It is a universe of flow. Rocks flow between planets. Comets flow between stars. Dust flows between galaxies. And on these currents, perhaps, flows the most precious and fragile cargo of all, the pattern of life itself. Whether we are the first to wake up, or whether we are the latest in a long line of star travelers, the truth is that we are not isolated. We are woven into the fabric of a cosmos that is constantly sharing its secrets, one stone, one spore, one molecule at a time. And if that is true, then looking up at the night sky is not looking into the void. It is looking into the mirror. If the idea of rocks carrying bacteria feels grounded in physics, a simple matter of collision and trajectory, then the next layer of the panspermia hypothesis requires us to look not at the solid stone, but at the invisible code of life itself. We must descend into the microscopic world of viruses and ask whether the software updates for evolution on Earth were written here or whether they were downloaded from the sky. This is the realm of viral panspermia, a concept that pushes the boundaries of biology to their breaking point. To understand why this is even a consideration, we have to look at the ocean. If you take a single teaspoon of seawater and look at it under a microscope, you will find millions of bacteria. But you will find something else in far greater numbers: viruses. There are an estimated 10 nonillion, that's 10 followed by 31 zeros, viruses in the Earth's oceans. If you line them up end to end, they would stretch past the nearest 60 galaxies. They are the biological dark matter of our planet. Viruses are strange entities. They occupy a gray zone between the living and the inanimate. They cannot reproduce on their own. They are essentially packets of genetic information, DNA or RNA, wrapped in a protein coat. They are data sticks waiting for a computer. On Earth, viruses are the drivers of evolution. They infect a host and often they kill it. But sometimes they do something different. Retroviruses, for instance, can insert their own genetic code directly into the DNA of the host. If this happens in a germ cell, an egg or a sperm, that viral code is passed down to the offspring. It becomes a permanent part of the species genome. We know this happens because we have found the fossils of these events in our own bodies. Roughly 8% of the human genome is made up of endogenous retroviruses, ancient viral infections that happened to our ancestors millions of years ago and never left. One of the most striking examples is a gene called syncytin. This gene produces a protein that allows cells to fuse together to form a layer. It is absolutely essential for the formation of the placenta in mammals. Without it, you would not have been born. And yet, the code for that protein didn't come from a mammal. It came from a virus. At some point in the deep past, a primitive ancestor was infected, and instead of dying, it co-opted the viral weapon to build a new way of reproducing. This is where the proponents of panspermia ask a shivering question. Did that virus originate on Earth? The strong panspermia hypothesis, championed by Hoyle and Wickramasinghe, suggests that the Earth is constantly bathed in a rain of viral material from cometary debris. They argue that the evolution of life is not just a slow Darwinian process of random mutation and natural selection, but a punctuated process of horizontal gene transfer from the cosmos. They point to the Cambrian explosion as a potential impact event, not of rock, but of information. About 540 million years ago, life on Earth underwent a sudden, radical transformation. For billions of years, the oceans were filled with simple, soft-bodied creatures, sponges, and mats of microbes. Then, in a geological blink of an eye, the world changed. Eyes, claws, shells, skeletons, and complex nervous systems appeared almost simultaneously. Darwin himself was troubled by the suddenness of this event. It didn't fit the slow, gradual model of evolution. But if the Earth had passed through a dense cloud of cosmic dust loaded with viral genetic material, it could explain the sudden injection of biological complexity. The software for complex eyes or hard shells might not have evolved from scratch. It might have been an install. There is a specific creature that often comes up in these discussions, an animal so strange that even mainstream biologists jokingly call it an alien. The octopus. Cephalopods, octopuses, squids, and cuttlefish are an evolutionary anomaly. They have large brains, complex camera-like eyes, and a nervous system that is distributed throughout their arms. They can edit their own RNA on the fly, changing their biology to adapt to temperature changes, a skill almost no other animal possesses. In 2018, a group of 33 scientists published a controversial paper suggesting that the sudden emergence of cephalopod complexity hundreds of millions of years ago is hard to explain with conventional evolution. They noted that the octopus genome seems to have exploded in complexity very quickly. They tentatively asked, could cryopreserved eggs or viral codes from space have contributed to this leap? While most of the scientific community rejected the idea as too radical, arguing that the octopus genome is weird but definitely terrestrial, the fact that the question was asked in a serious journal shows how the lines are blurring. We are beginning to realize that biology is information technology, and information can travel. If viruses can survive the vacuum, and we know they are tough, then they are the perfect cosmic messengers. They are small enough to be shielded by dust grains. They are light enough to be pushed by solar winds. They require no energy to survive the trip. They just wait for a compatible host. This perspective turns the galaxy into a giant open-source coding project. Genes that evolve on a planet around Betelgeuse could eventually find their way to a swamp on Earth, inserting a new subroutine into the biosphere. We might share genetic code not just with the monkeys and the mushrooms, but with life forms we have never met, separated from us by 1,000 light years. But if the galaxy is buzzing with rocks, comets, and viral codes, if the seeds are raining down everywhere, we are forced to confront the loudest, most terrifying silence in human history: the Fermi Paradox. The Italian physicist Enrico Fermi famously asked, "Where is everyone? If the universe is old and life is common and space travel is possible, we should have been visited by now. Or at least we should hear their radio signals. We should see their megastructures." Panspermia makes the Fermi Paradox much, much worse. If life on Earth was a miracle, a 1 in a trillion accident of chemistry that happened only here, then the silence of the universe makes sense. We are alone because life is hard. We are the only lottery winners in a galaxy of empty tickets. But if panspermia is true, life is not hard. The ingredients are everywhere. The delivery systems are automated. The seeds are hardy. Life should be popping up on every wet rock in the Milky Way. The galaxy should be teeming with biological noise. So why is it quiet? This brings us to the concept of the Great Filter. The Great Filter is a barrier, a hurdle in the development of life that is almost impossible to overcome. It is a step in the ladder of evolution where almost everyone falls off. For us, the most critical question is the filter behind us or ahead of us? If the filter is behind us, it means the hard part was the origin of life itself. Or perhaps the jump from single-celled slime to complex animals. If that's the case, then panspermia might be wrong or very inefficient, and we are special. We are the chosen ones who made it past the hurdle. But if panspermia is correct, if life starts easily and spreads everywhere, then the filter cannot be the origin of life, cannot be the simple existence of bacteria. It means the galaxy is likely full of slime worlds, planets covered in moss and microbes that never build radio telescopes. Or darker still, it means the filter is ahead of us. It means that civilizations rise, they discover technology, they listen to the stars, and then they die. Maybe they destroy themselves with nuclear weapons. Maybe they consume their planet's resources. Maybe they create artificial intelligence that replaces them. Or maybe they are wiped out by the very mechanism that brought them life: cosmic violence. asteroids, supernovas, gamma-ray bursts. If panspermia is true, we are living in a graveyard. The seeds land, they bloom, and then they wither before they can speak. The silence of the night sky is not the silence of an empty room. It is the silence of a library after closing time. This thought can feel heavy. It makes our existence seem fragile, almost accidental. But there is another way to look at it, a way that brings us back to the light. If we are the product of a cosmic system, if we are the survivors of the journey, the beneficiaries of the comets, the inheritors of the viral code, then we have a responsibility that goes beyond this planet. We are the part of the universe that has become aware of itself. We are the mind that has finally awoken after billions of years of slumbering in the rock. And we are about to do something that no rock, no comet, and no virus can do. We are about to become the agents of panspermia. We are already leaving footprints on the moon. We have sent rovers to Mars. We have spacecraft exiting the solar system. In the next century, if we survive our own great filter, we will likely send probes to the stars. We will carry the library of Earth's life, the DNA of plants, animals, and humans to new worlds. We will become the Sours. We will be the mechanism by which life jumps the gap to the next star system. Perhaps this is the ultimate purpose of intelligence in the cycle of panspermia. Nature can only throw rocks so far. Gravity has its limits. To cross the truly vast distances, to cross the galaxy, life needs to build a ship. It needs to build a mind. Maybe we are not just the passengers. Maybe we are the pilots. As we come to the end of this journey, let's return to where we started. Step outside again. Look up at that vast, three-dimensional ocean of night. When you look at the stars now, don't see them as distant, alien fires. See them as the furnaces that forged the iron in your blood. When you feel the wind on your face, don't just feel the air of Earth. Remember the comets that brought the water in that air, falling from the deep freeze of the outer dark. When you look at your own hand, don't just see flesh and bone. See a library of genetic code that has been written, edited, and rewritten by billions of years of survival, shaped by viruses that may have fallen from the sky, built from amino acids that formed in the silence of a nebula. The theory of panspermia asks, did we come from space? The answer, in every way that matters, is yes. We are not on the Earth. We are of the Earth. And the Earth is not separate from the galaxy. It is a breath of the galaxy, a momentary gathering of dust and light. We are the travelers. We are the ancient aliens we have been looking for. We have been wandering for billions of years, changing shape, changing vehicles, moving from star to cloud to rock to ocean to land, until finally we stood up, looked back at the sky, and wondered where we came from. The answer is written in the dust of Murchison. It is frozen in the ice of the comets. It is sleeping in the red dirt of Mars. And it is beating in your chest right now. You are the universe, and you are finally home. Thank you for joining me on this journey into the deepest mysteries of our origins. If you found comfort or curiosity in this story, and if you want to support this little corner of calm in the digital noise, please consider liking the video and subscribing to Mysteries Beneath Earth. Sleep well and keep looking up.